Okay, so this time we've got a racetrack, and it's designed with two different bankings. So on the inside, the car can corner at 80 kilometers an hour, and those on the outside can corner at 160 kilometers an hour. So in both cases, they have no tendency to slip. We like seeing that. If the inner radius is 200, outer radius is 220, what's the difference between the angles? So what's the angles in the track? So again, what we do, we set up, this is what both of them would look like at different. But remember, we're going to have two, but they'll have the same ideas though. We want to work out what tan theta. So we do the same things we've done before. N cos theta is equal to mass times gravity, and the normal force times sine theta is equal to mass times velocity squared times r. Dividing, we get tan theta is v squared on r. But so in the first situation, at 80 kilometers an hour, that works out to be 22 meters per second. Remember, we're working in meters per second because we've got 200 meters our radius, and our gravity is 9.8 meters per second squared. So that means tan theta in that case, so we give it a subscript of 1, it gives us 0.25, which gives us 14 degrees at that. So the inside of the track is banked at 14 degrees. Then to go 160, then, well, that means it's going to be at 44.4 meters per second. But our radius is 220 meters per second, 220 meters this time. So we put that in, we get 0.916, which means our angle becomes 42.4. There's a difference at 28.4. So it's going at 14 degrees, but then it goes steeper later on. Maybe not that steep, but 42.4. Hopefully you get the idea. You can go faster as long as it's steeper in that case. This time we've got a railway line taken around a circular bend of 1,000 metres. And the distance between the rails is 1.5 metres. So at what height above the inner rail should the outer rail be raised in order to eliminate lateral thrust? So again, as a train goes around a bend, because it goes around a bend, it wants to move off in that tangential movement. It wants to fly out. So to eliminate any friction there that's been put on the rails, the train will be tilted. Now, it doesn't have to be tilted much, and as you'll see in a moment. So what we look at is what does it have to be there? And what is the difference? What a height does the outer rail need to be above the inner rail to get that angle there? So what we're playing with, again, this is what's going to be happening on the rails there. So we're going to have this situation occurring. So we get the n sine theta mv squared on r, and we get tan theta v squared on rg, like we have. So again, we work out what tan of theta is going to be. So kilometers per hour means 11.11 meters per second. Radius is 1,000 meters and 9.8. So it gives us tan theta being equal to that value. So what we're looking at here is that because the outer rail's got to be above the inner rail, okay, the angle that we just got there was tan of theta. We didn't work out theta. We just got tan of theta as 0.0126. And the reason being, so it's not going to be very big. That's 1.5 meters. If we looked at that number and worked out in this triangle, we get H on L would be equal to H on L there is equal to sine of theta. Now we know when the angle's small, and the angle is going to be small here, sine of theta and tan of theta is basically equal to theta. So if that's the case there, we could say that H would be, instead of H, the height being equal to L sine theta, sine theta and tan theta, when it's going to be small, is going to be the same. So instead of doing a little bit more calculation, we just say, well, H equals L sine theta be the same as L tan theta, which is the 1.5 times 0.0126, which is 0.01989, which works out to be 18.9 millimeters. See how small we're talking. It doesn't have to be raised very much. But by raising it 18.9 millimeters, so just under 2 centimeters, which is not much at all, it starts to get rid of that lateral thrust. So that friction that acts upon the outer rails starts to dissipate, because it's just the height of the outer rail is just above the inner rail. Now, I don't know if you've actually noticed that on a train. It's a bit hard when you're walking in the city. It doesn't do it very often. You don't see that much of it. Best ones are when you see this in a country. If you're traveling around the country situation on a train, and you're at the back of the train, and you see it going around a bend, you can actually see the front of the train really clearly as you look out your window. You do start to see that, because it's going around a bend. You do see that tilt. You can't have it too tilted, because again, it's comfort of the passengers inside is important as well. So your bend can't have that smaller radius that it has to be really tilted. But they will have design speeds depending, and it can, again, faster if they are able to tilt it slightly. And this is only slightly. Same idea here. We've got a railway line that's been constructed around a circular curve, radius 500 metres. So the smaller your radius, the more it needs to be tilted for you to go faster. The distance between the rails is 1.5, and the outside rail is 0.1 of a metre. So that's significant. 0.1 of a metre is 100 centimetres. Sorry, no, it's 10 centimetres, not 100 centimetres, because that'd be 1 metre. We want to find the speed that eliminates the sideways force. So basically we're looking at what's its design speed. How fast would it actually have to go to avoid slipping? Either way, because it's raised 10 centimetres on the outside to the inside, there would be pressure on the inside rail if it's not going fast enough. But if it goes too fast, there's pressures on the outside of the rails to go outside the rails. So there's pressures either way, unless we get that speed right. And train drivers would know. They'd have indications of what would be the design speed as they're going around the bend. So this time we've got our dimension diagram. We can see our height there. We've drawn it all together. So our height there, our distance in the rails, and what the reaction force would be. There's our reaction force that's happening. And there's no friction if we're getting the speed right, if we're getting that velocity. So the mass times gravity there, and again we can set it up. We know that we've got T cos theta is equal to m mass times gravity, and T sine theta is equal to mv squared on r. So we get that tan squared theta is equal to v squared on rg. Now from this though as well, we know that h on d, as we did before, the d squared minus square root of d squared minus h squared. So applying Pythagoras' theorem here, we get tan theta there. And we can put tan theta in there. So v squared equal rg h square root of d squared minus h squared. And we know all those. We know what d is, we know what h is, we know what r is, we know what the gravity is as well. So we do that substitution, and we're able to find that the velocity would be 18 meters per second. So that's how far the train needs to go to eliminate any forces of friction that will act inwards or outwards. So to move without any sideways force. That's going to have to be our speed that's designed to do.